So the first step that you want to do is wear goggles and put on gloves, and then you want to rinse the burette with DI water, and then rolling the burette around to make sure that you contact all the surfaces with the DI water. Then you want to take your solution, which is our 0.1 molar sodium hydroxide, and clean the burette out with that, doing the same thing, rolling the burette to allow contact of all of the burette with your sodium hydroxide. Now the next step is you want to take your sodium hydroxide and fill your burette using a funnel up to the 10 milliliter point, but nowhere above that, so you can have an extra amount of significant figures. You then drain out a portion of your sodium hydroxide in order to clean out the tip of the burette into a waste beaker. And you want to read the volume of your burette using a white paper in order to see the meniscus. So the next step is to take your 0.1 molar acetic acid from your stock solution and pour it into a beaker so you can pipette a certain amount into your Erlenmeyer flask. So we are pipetting 10 milliliters of the acetic acid, and you want to record the volume that you pipette to the 100th place. The next step is to add 3 drops of phenolphthalein, which is a color indicator. It is colorless at acidic pHs, and then it shows a color when the solution becomes basic.
So this is how you find the volume at the equivalence point. It's not something you need to do at the beginning, but I like to do it initially. So we have 10 milliliters of 0.1 molar acetic acid and 0.0922 molar NaOH. So we use this equation to find the volume of the base that's added at the equivalence point. So we have 0.1 molar acetic acid, and we have 0.01 liters of the 0.1 molar acetic acid, and we divide it by 0.0922 molar NaOH to get 0.010845 liters. Multiply that by 1,000 milliliters to get 10.85 milliliters, which is the volume of base added at the equivalence point.
Alright, so here we're doing our trial titration, and you always want to do that to estimate where your endpoint is. So what we do is we open the stopcock on the burette and allow the sodium hydroxide to pour into the acetic acid, and you want to stir every now and then to make sure that the hydroxide and hydronium are interacting with each other. And you want to continue to do this until a color appears and stays for longer than 10 to 15 seconds. So now we've reached our endpoint, and we want to record the final volume on our burette.
So this equation is going to give us the pH of the solution without, or before any NaOH is added. So the VB is 0 milliliters. So we're going to be using this equation, which sets Ka equal to x squared. X squared is, keeping in mind this equation, it's both of the products multiplied by each other over the concentration of the acetic acid. So when we plug in what we have, we get 1.75 times 10 to the negative 5th, which is the Ka, equal to x squared over the concentration of acetic acid. And this is the algebra, so it's going to be the square root of 1.75 times 10 to the negative fifth times 0.1, and that gives us x to be 0.001322, which is the concentration of hydronium ions in the solution. So we take the negative log of that to get the pH. And then we can add this to our titration curve, where the pH is 2.88 at 0 milliliters of NaOH added.
So here we're performing our second titration, and we first start with just pouring in 2 milliliters of our sodium hydroxide.
So this is the point where 2 milliliters of NaOH have been added to the flask. So we are going to calculate for the pH. We will be using the Henderson-Hasselbalch equation, but in order to use it we need to find the moles of base and the moles of acid. So we do that by multiplying the molarity of acid by the volume to get 0.001 moles of acid, and the same for the base, so 0.0922 molar times 0.002, because at this point we have 2 milliliters of base added to get this many moles. And then we're going to subtract the moles of base from the moles of acid, because at this point, after 2 milliliters of base has been added, this is how many moles we have in the flask. Then we can plug this amount of acid and this amount of base into the equation. But at this point we also need to solve for pKa, and we do this by taking the negative log of the Ka, which gives us 4.76. So in the equation it's 4.76 plus the log of the moles of NaOH over moles of acetic acid to give us a pH of 4.11, which ends up right about here on the titration curve.
Now we've added more of our sodium hydroxide up to the volume of half of the equivalence point.
Now we're at the simplest of all equations, and that is when the volume added is at half of the equivalence point, which in this case is 5.43 milliliters. So at the half equivalence point, the pKa value is equal to the pH. Therefore, 4.76 will be our pH, because that's also the pKa value, and that will end up around here. On our titration curve.
So now we've passed half of the equivalence volume, but have not yet reached the end point. So we're at 8 milliliters of sodium hydroxide into the solution.
So at this point, we've added 8 milliliters of NaOH. So we need to, first of all, find out how many moles of base we have at this point. So we're going to take the molarity, 0.0922, and multiply it by the amount of base that's been added, which is 8 milliliters. And we're going to subtract that from the initial moles of acid to give us 2.62 times 10 to the negative fourth moles of acid, which we will plug in to the Henderson-Hasselbalch equation once again. So we take the pKa, which is 4.76, plus the log of 7.38 times 10 to the negative fourth moles of base over 2.62 times 10 to the negative fourth moles of acid, which gives us a pH of 5.21, which lands right about here on the titration curve.
So now we are very close to our endpoint, and we want to add the sodium hydroxide in drops in order to not pass the endpoint. So drop by drop we add our sodium hydroxide and make sure to stir very well in between each drop until we reach our endpoint. There it is right there. Now we want to make sure that we read the final volume on our burette.
At this point, we've reached the equivalence point, which means that 10.85 milliliters of NaOH has been added. And at the equivalence point, moles of base equal moles of acid. So we need to do a calculation to find out the concentration of the acetate ion in the solution. So we do that by multiplying the volume of base added, so 10.85 milliliters, by the initial concentration of the NaOH, which gives us 0.001 moles of the NaOH, and then we're going to divide it by the total volume, which at this point is 20.85 milliliters, to give us 0.0476 molar of the acetate ion concentration. And so also at this point we need to, since we're at the equivalence point, we need to start using the Kb, and we find the Kb by dividing the Kw, which is a constant, by the Ka, to give us 5.71 times 10 to the negative 10th. And we're going to plug that in down here in this equation, where we set it equal to x squared over the acetate ion concentration, solve for x, which is 5.21 times 10 to the negative 6th. And then we're going to plug that in to the negative log equation to give us 5.28. Now that's the pOH, so we need to subtract the 5.28 from 14 to give us a pH of 8.72 at the equivalence point, which ends up here.
We then added 0.2 milliliters of sodium hydroxide to our solution.
So at this point we've entered region 4 on our titration curve, and we've added 11.05 milliliters of base, which puts us 0.2 milliliters past the equivalence point. So we need to calculate the amount of excess base we have, or excess OH. So we do that by multiplying the amount of NaOH added, which is 0.2 milliliters, by the concentration to get 1.84 times 10 to the negative 5th moles of excess NaOH. So then we divide it by the total volume, which is 21.05 milliliters at this point, to get the concentration of excess OH minus. We then take the negative log of the excess OH to get the pOH of 3.06, and then we subtract that from 14 to get a pH of 10.94, 0.2 milliliters past the equivalence point, which puts us around here, pH of 10.94 on the titration curve.
And lastly, we added 3 milliliters after the endpoint of sodium hydroxide to our solution.
Okay, so here we are in the last point in region 4 on the titration curve. At this point we've added 3 milliliters past the equivalence point. So total we've added 13.85 milliliters of base. So same exact process as the last equation, just different numbers. So we have 0.003 liters of NaOH added because we are 3 milliliters past the equivalence point, multiplied by the molarity of the NaOH to give us moles of excess NaOH, which we divide by the total volume, which at this point is 23.85 milliliters, to give us 0.01161 molar excess OH. And we use this to find the pH by plugging it in. So we take the negative log of the concentration of excess OH, which gives us a pOH of 1.935, which we subtract from 14 to give us a pH of 12.07, which is our last point on the titration curve. So here we have our final titration curve with all of the points. Region 1, which is pH 2.88, is our weak acid equilibrium. Region 2 is these 3 points, pH 4.11, 4.76, 5.21. In region 2 we have unreacted analyte, it's a mix of the acid of the conjugate base, which is a buffer. Buffer resists change in pH. Then we move into region 3, which is the equivalence point, where we're at weak base equilibrium. And then once we reach the equivalence point, we're into region 4, where we have excess OH.
And all the solutions may be rinsed down the drain with an adequate amount of water. And that's the end of this module.